It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, welcome to the next video for topic 4. This is 4.4a, which is on polymers. So there's a couple of sections in this topic. There's polymers, there's metals, and there's recycling as well. So for this one I'm just going to try and fly through some of the stuff about polymers. There are some more dedicated YouTube videos I've created that explain some of the details in more depth, but hopefully this will give you a quick overview. So basically a polymer is a large molecule, right? The word poly means many, and the word mer comes from the word monomer, which is a small molecule. So we have lots of small molecules like this. So this is obviously these are small plastic parts, but these are all polymers. But imagine all of these, we link them up into a really long molecule, and that's what we call a polymer. If we make it from only one monomer, that's called a homopolymer, and if we make it from two or more, it's called a copolymer. Excuse me. Alright. So, there's two types of polymers you can have in terms of their properties. Alright, so there's you can have a homopolymer, which is made up of one monomer, and a copolymer, which is made of two or more. But if you're talking about actual types of polymers, there's what we call thermoplastic and thermosetting. Now, thermoplastic polymers are characterized by this sort of characteristic. Okay, so they have no cross-linking. So you have all these long polymer chains, and there's no sort of cross-linking or covalent bonds holding them together. So the way I say to understand this is it's like a bowl of spaghetti. We've got all the thin strands, so they're all interconnected, but it's really easy to pull the strands apart. Now, the benefit of that for thermoplastic polymers is that they can be recycled, hence the recycling symbol here. Okay, so a thermoplastic polymer is characterized by the fact that you can melt it, okay, and reform it into a different shape, which means they're recyclable. Whereas a thermoset polymer, however, has lots of cross-links between them. So I liken this to like a brick wall, for example, where all the bricks are locked in together and there's lots of strong bonds between them. Similar sort of thing with a thermoset polymer. These generally have a much higher melting point. They're a lot stronger. So you can see here, this like kids' plastic table set is a much stronger, sturdier plastic. But when you melt this, it doesn't go runny, it just blackens, because what you're doing is basically decomposing it. You're breaking the primary bonds in here, you're destroying the structure, and it chars. Okay, so that's when it goes black. So we say that these cannot be recycled. So I've kind of just tried to summarize this all here, and in case you can't quite see that underneath, just summarizing that, no, we cannot recycle the thermoset polymers. Okay, but one of the real benefits of plastics, however, whether they're thermoplastic or thermoset, is that they can be tailored for almost any function. Which is really useful. So you can adjust their resistance to heat, you can adjust their density, their resistance to chemicals, their colour, their shape. It's really, really useful to have that property, which is why plastics are probably the most widely used thing within the world. Right? And they've been used to replace a lot of other natural things we used to use, like wood and metal, because they're much more versatile. So the way that we make polymers, there's two ways. The first one is called addition polymerization. So with addition polymerization, we have two or more monomers and we add together across a double bond, and we don't eliminate a small molecule. So I've actually gone through and I've done a YouTube video here, which you can see the link for. It's just called addition polymerization, and I'll go through this in a little bit more depth and show how we actually add across the bonds, and how you actually draw the repeating units and how you add the molecules together. So I'm just going to show a couple of examples here then. So polyethylene, this is an example of polyethylene here. The bag, obviously not the vegetables inside, but the bag here is polyethylene. Okay, so it's quite a stretchable material, this one. There's two types of polyethylene, which I'll talk about in a minute. But basically we use the monomer ethene. So it's really easy to work out what the monomer is because it's just the second part of the name. So poly means many, ethene molecules together. So ethene is just two carbon atoms with a double bond between it. What happens, and I'll see if I can get my pen to work at the moment. So what happens is that one of these bonds breaks, and this bond is made up of two electrons. Okay, every bond is made up of two electrons. So what happens is that this electron goes over here into the middle, and this bond here is made up of two electrons as well, and this electron goes into the middle here. now that we've got 2 electrons, what we can do is we can form a bond between them. We can form another bond here, and obviously what's happened is we've broken the double bond in the middle, which is why you end up with this molecule like this. Now, anytime you see these square brackets, what that means is that is the repeating unit. So that is the part that repeats itself over and over. So that's one ethene molecule, there's another one, there'll be another one over here. So that's the basis of polymerization, where you add across a double bond. So each of your species over on the sides, so we'll go to red here, so all these hydrogens you can see through here, we carry these through into the molecule here, okay, just above and below where we had the double bond. So it's really easy to draw the molecule, draw the polymer from the monomers when you just keep your carbon-carbon double bond in the middle of your polymer chain here, okay, and then what you do is you just put the other bits that were on the monomer on either side of it. So polyethylene is also sometimes known as polyethylene. It's about 100,000 carbon atoms long, so if you work that, it's about 50,000 ethene monomers added together. And you can see it's used for a whole bunch of different things: plastic bags, glad wrap, which is sort of what we're seeing here a little bit, clothing, kites, maps, protective clothing. So I did mention there are 2 types. So that's what we call high density polyethylene. So high density polyethylene has the chains spread apart. Okay, high density polyethylene has the chains close together. I'll get it right, sorry guys. That's the reason, because there's no branches on the chains. Okay, so what that means is that the chains can stack really close together. So liken it to Pringles chips. Okay, so they're all nice and flat, there's no branches, so the Pringles chips just all sort of stack on top of each other. That means there's a lot of them in a small area, which means it's high density. Okay, now what that means is you've got a greater number of secondary bonds that occur between these chains, so it gives it a higher melting point and strength. The other side of it is low density polyethylene. Because you've got these chains between them, they don't form as many bonds between each other. So I liken this to like Smith's crinkle cut chips, for example. So where you've got those sort of ridges on it, right? You don't get as many stacking on top of each other nicely as you would with Pringles. So there's less per unit area, which means that you get less secondary bonds occurring, which means it's a lower boiling point. The benefit of that is, though, because there's less parts holding it together, you get a more flexible plastic. So this is an example of glad wrap. So you can get glad wrap that really is very flexible and can wrap around things, as opposed to high density polyethylene, which is more like your glad bags, you know, those sandwich bags you put things in. They're not stretchable, they don't flex around things. Both polyethylene, but different properties based upon the secondary bonding you get between the chains. A couple of other ones. Very common one is polyvinyl chloride. So you can see here we've got plumbing pipe. Is very commonly made out of PVC is the shortened term. So we use vinyl chloride. The only difference is that you've got a chlorine here instead of a hydrogen. Now the difference that makes is between the chains you've now got something that has 17 electrons here instead of 1. It makes your secondary bonds between the chain much stronger. So the result for that is a much harder, firmer, stronger plastic, because you've got stronger secondary bonds occurring between the chains. Rubber is my personal favourite. I couldn't help but just put in one rubber ball here for Adelaide Crows, best football team. We won't talk about any of the recent games they've played, but that's alright. They're still doing really well, and I'm sure they'll come back once all their injuries are over. Anyway, enough about football. Rubber is made from the monomer isoprene. So there's 2 kinds of ways that this can actually add. The first one is, you can see here you've just got a double bond, so we add across that double bond, and this is actually one of the side chains. So we call this, so that's 2 carbons, 3 hydrogens, C2H3, and you can see that over here. So all we've done is add across the double bond as normal. There's the methyl group underneath, which is the other part of it, and here we get a rubber polymer chain. The good thing about having this double bond in here is you can form secondary bonds to other rubber chains, and it allows it to be really stretchy, which is why we get that elastic band kind of stretch because of the rubber molecules. We normally have about 1,000 to 5,000 repeating units, and if you replace that CH3 group up here with a chlorine molecule, you make a oil-resistant rubber, which is what they'll use in cars for head gaskets. And if you replace that with a hydrogen atom, you get my personal favourite, super bouncy rubber balls. Okay, so very versatile monomer you can use here, isoprene, and when you change a couple of the side chain parts on it, you can make very different rubber, which is very, very useful. You can also add it a different way. So what happens in this way is that one electron goes from here towards the middle, and one electron goes from here towards the middle to create this double bond here. Okay, and then the other electron from here goes out this side, and this one goes out this side to form a new bond to another isoprene monomer. And this time you end up with a very, very different polymer chain to the one before. You don't get this sort of elasticity between it, but this double bond is really useful because that's a reactive site. So what we can do is we can actually add sulfur across that, which is actually S8, and that sulfur can be added between the chains to start giving them sort of that flexibility. And the good thing is that with those sulfur atoms, when they flex, they snap back into position. That's why we can get rubber bands like this. That process of adding sulfur across the double bond here is called vulcanization. Okay, so vulcanization is, you hear it sometimes referred to in terms of sulfur coming out of volcanoes, because volcanoes produce a lot of sulfur. That's why we call it vulcanization. So to show you what that looks like, here we've got our two polymer chains. We've got our sulfur, which is S8, that comes in and adds across between the chains. Okay, and you get these cross links, which, as you said, are quite stretchy. However, as you add more in, okay, you add more and more in, and what you do is you start to link these all these polymer chains by lots of strong covalent sulfur-sulfur cross bridges, and that turns it into a thermoset polymer, which becomes very hard. So you turn it from a rubber band into something like a car tire. Okay, and you reduce the elasticity and you improve the strength of the rubber. So that's really, really useful. You can tailor the rubber's strength to what you want by how many sulfur-sulfur cross links you add. Okay. Now, obviously the downside of doing this is that when you try to recycle rubber, you'd need to heat it. As soon as you heat it, you're going to be releasing sulfur dioxide because of these cross links, and that obviously has a huge amount of problems in terms of environmental chemistry, acid rain formation, and so on. Another one that we use quite a lot is polystyrene. Now, polystyrene is very, very different from the others. What we're doing is we're adding in this benzene ring, which is C6H5. Now, that's a very, very big, bulky structure. So what that does is it makes the chains actually separate apart, so you get a lot of distance between them, a lot of air between the chains, which is why we end up with a really lightweight material like we do here with this. Okay. So that's addition polymerization. Condensation polymerization is where two or more monomers add together with the elimination of a small molecule. So it doesn't have to be across a double bond anymore. Okay, and this time we eliminate a small molecule. So generally we'll use two main types of polymerization we're going to be looking at. A polyester polymerization requires the formation of an ester. So an ester requires an alcohol group and a carboxylic acid. Okay, and when we add these together, what happens is that we eliminate, oops, sorry, I didn't actually change the color on this. Let me see if I can do this. There we go. We eliminate the OH from here and the H from here. Okay, they come out and that forms water. Now, common misconception here is that this is called condensation polymerization because we're producing water. That's actually not the case. The reason we call it condensation polymerization is because the bonds here between the carbon and the oxygen, which comes off of the alcohol, actually shortens in length, and so it condenses, and that's why I call it condensation polymerization. Because it doesn't always have to be a water molecule that's eliminated. That's usually the case, but it's not always the case. So it's not condensation polymerization because we're eliminating water. We're eliminating a small molecule. But you can see here, and I'm just going to move myself up here at the moment, okay, is that here we've got our long, this is our polyester, and you can tell it's a polyester because there's an ester functional group in there. As soon as you see an ester functional group in there, it's a polyester. So an easy way to do this is you just basically, let's see, I might just get rid of this drawing that I put on there if it's going to let me. It's not. Okay, I'll show you on the next slide how we do it. Okay, sorry about that, just had to go and fix my pen wasn't working. So the easy way to do this is to break your ester bond here. So here's the carbon-oxygen which is formed in the ester bond, and so what you do is you then go to the spot where you next find that same bond, which is there, and you'd find it also over here on this one. And so you end up with excuse me, one monomer here and another monomer here, and then you just convert them back into the alcohol and the carboxylic acid functional groups that you can see down here. I'm not going to go into too much depth. What I'll do is I'll just go back to the previous slide, and if I move this down, you can see I've got a video here which I've done all about condensation polymerization as well, which you can use if you need to be able to go through and make sure you can draw all the structures of the polymer. So I strongly recommend that you look at that one. Okay, so just some examples, and again I'm just going to move myself here so you can see everything, sorry. So a polyamide is made from a diacid or a diamine. So again we're using a carboxylic acid group like we did for the polyester, but this time we're using an amine. So I'm just going to draw a primary amine there, but you can actually use a secondary or tertiary amine in rare cases as well. And so what happens is when these combine together, again we eliminate a water molecule, so we eliminate an OH from here and a hydrogen from there, and that eliminates a water molecule. And what that creates is this functional group, okay, which is a amide, okay, and so it will go on from this way. So actually I should probably create this. Normally you'd have another bond over there, sorry, which I left off. But this is our amide group, and you can see it here within polyamide. So as soon as you see the carbon-nitrogen bond like that, you know that it's a polyamide, and you can see the two monomers we've used down here for it. So just a couple of examples of some condensation polymers. Nylon was the very first completely synthetic polymer ever made. It's about 1960s or something, I think, and it has lots and lots of different amide functional groups. Okay, nylon is used in carpet clothing, ropes, bearings, so these sorts of nylon ropes are very common. This nylon here, if you can see it, this one here, this has a specific name. It's made from octan dioic acid and hexane 1,6-diamine. Okay, so this is actually called nylon. Any ideas? It's called nylon 6A. Alright, because it comes down to the number of carbon atoms. So there's 6 carbon atoms here, and there's 8 carbon atoms along here. So this is called nylon 6A, and you can just vary the length of the carbons in that chain to vary the properties of your nylon. So, like I said, condensation polymers eliminate a small molecule, and whether it's a polyamide or a polyester, for both of them you eliminate a water molecule. So you should be able to draw write the equation for that. Alright, talked about the repeating unit in here, and again I've talked about it in the video, so I'm not going to go through in too much detail, but make sure you understand what the repeating unit is, so you can see for each of these here how you start with your monomer on the left and you end up with your polymer on the right. Okay, so you can see these are all examples of addition polymerization. You can tell that because you start with a double bond between carbon atoms for your monomers, and so what we're doing is we are removing a single bond out of there, and so removing the double bond to make a single bond, as you can see, and we're just keeping each of the species on either side of it. So that's just an example of how you go from the monomer to the repeating unit pretty quickly, and we use the N here to represent any number of repeating units. So we have like 50,000 of our monomers, and we end up with 50,000 repeating units there. You can do it for both addition polymerization and condensation polymerization. I suggest you have a look at the video, make sure that you know how to do it. Alright, natural polymers have been around for thousands of years. There are plenty of examples. So silk, so coming from silkworms, for example here. Wool, DNA is an example. DNA is made up of a long polymer, and proteins are also polymers. They are sometimes called polypeptides, so that's another example. Cellulose you find in plants, that's an example of natural polymers as well. But the reason we make synthetic polymers is because they have so many different versatile uses that we can create within them. So the properties can be adjusted for any number of things. So this is the example of superglue. So this is the monomer that you use for superglue. This is the polymer chain, I should say. That's not showing all of it, but it kind of continues along, and that occurs when you get a polymerization reaction occurring to form a very hard, durable, solid polymer, quite different from some of the other ones that we're looking at. You can make polymers recyclable. Natural polymers tend to just wear out. With synthetic polymers, you can recycle them if you need to, and you can use them for a wide variety of purposes. Some of the disadvantages, however, is that they're made from non-renewable resources. So this is something which is really coming up recently in the world, and this is looking at the plastic island. So this is actually in the Pacific Ocean, I think, or if you understand my writing, the Pacific Ocean. Sorry about that. It should be the Pacific Ocean. This is actually a massive island of just plastic, and it is really big. Okay, and there's lots of issues around it. I think it's like somewhere off the coast of the Caribbean or something like that. Might be around Honduras, somewhere there in the Pacific Ocean. And it's just all this toxic waste that stretches for miles and miles. It is massive, really massive. They're saying that it's basically equivalent of like a state in size in some places. So it's really a big issue that we're facing, obviously. In Australia, we're better at disposing of our plastic into landfill if we can't recycle it. So that's some of the disadvantages. We do use non-renewable resources like oil because we're using hydrocarbons. So obviously that takes away from fuel reserves. That can be hard to recycle. And if we do get them into landfill, they release toxic chemicals. And obviously if they form things like this in the ocean, they form a massive risk to marine organisms and ecosystems. So what we're trying to do these days to try and combat this is start to use biodegradable polymers. So biodegradable polymers are designed to not take up landfill, but to be broken down after having been used. They usually break down due to either oxidation or hydrolysis, okay, or the presence of sunlight. So having polymers that can break down in the presence of sunlight is really useful within landfill in particular. Microorganisms hydrolyze the amide or estolates. What that means is they basically just add the water back in. So when we're doing a condensation polymerization, we took water out. In this case, what we're doing is we're putting the water back in to break it back down to the original monomers. If a carbonyl group is present, like a polyester or polyamide, those can absorb sunlight and also be broken down. Now the advantages of those obviously is that they are made from organic material rather than petrochemical stocks. They're not using up our fossil fuel supplies. They break down much faster in the environment and do not release toxic chemicals when they do break down because they're just breaking down into their initial or original organic materials. And particularly the real benefit at the moment is they're looking at the fact that these break down and can be specifically targeted to break down over a certain period of time, that they're really using this within a pharmacy to develop drugs that will go into the body. And so normally what happens is when you ingest a drug, it breaks down and absorbed into your bloodstream. What they're looking at is actually drugs that will delay in their release into the body, and drugs that will therefore have an effect for a number of weeks rather than just a couple of hours. So it's a really, really exciting, interesting area that they're looking at researching, and yeah, lots of money to be made in the biopharmacy area as well if you're interested in a future career in chemistry. One of the disadvantages is if they do go into landfill, for example, and they get covered over so they don't get exposed to sunlight or oxygen and water to allow the microorganisms to grow and break them down, then obviously they're about the same as normal plastics. So you need to have something in place to allow that degradation or hydrolysis to occur. Alright, so hopefully this has been pretty straightforward for you. As always, if you've got any questions, just ask. Alright, thanks guys.